Hello, Physics Nation. My name is Nate Larmond, and I'd like to analyze this pulley system. A bunch of pulley systems, actually. This is a two-pulley system, but we had 6 stations. So we went from a single to a double to a triple, all the way up to a 6-pulley system. And, well, let's talk about the 4 basic measurements of all simple machines, actually. We've got the input force. This spring scale is measuring how much uh, downwards force I'm applying with my hands. It's hard to read, but this is about 6.5 newtons. And the motion is called the input distance. So the spring scale is the effort or the input force, and how far my spring scale is moving is the input distance. The product of those two things is the input work, or the energy I'm dumping into the pulley system. The output work is the gain in gravitational potential energy of this load going up on the left-hand side. This is a kilo, so that's 9.8 newtons. And once you measure the distance the spring scale moves and the distance that the load moves, you can do all these interesting calculations. Like I said, work is one interesting calculation. The energy you dump in, where is that? Right here. It's just the input force multiplied by the input distance. So I moved the spring scale half a meter for all of my trials just to keep it constant. Let's see, I'm lifting 9.8 newtons, and well, it took about 9.8 newtons, 9.6 in the single pulley system. It's just a mechanical advantage of 1 or a little bit greater than 1. We'll talk about all the finer points of this experiment maybe later. Anyway, if you just do the input distance, half a meter, multiplied by the input force, roughly 9.8 newtons, you get the input work. So half of 9.8 is 4.9 or 4.8, as you can see. So I put in 4.8 joules of work. Well, what did I get out? Well, the load went up. So the load weighs 9.8 newtons, and it went up 0.41 meters. So the weight doesn't start at 0. You just have to read where it is. You put a little meter stick vertically next to the weight, and I went from 11 centimeters to 52 centimeters. So let's see the change in height. Let me just make this a little bit bigger. There's the change in height, 52 minus 11, or 0.52 minus 0.11 is 41 centimeters, or 0.41 meters. So if you do that distance multiplied by the weight, or the output force, or the load, you get about 4 joules, 4.02 joules. And the efficiency is the output work divided by the input work. So for the single pulley system, it was pretty efficient, 84% efficient. And then we have 72% efficient, 77, 71, 74, 85. Looks really confusing. Interpreting a list of numbers or a matrix like this can be tricky, and so we graph it. Yeah, so here's the number of support strings, our independent variable, as we shifted from a single to a double to a triple. How did the efficiency change? Well, this is the slope of my trend line. Looks confusing when a spreadsheet displays it, but it's just scientific notation. So the E means times 10 to the minus third. Pardon my sloppiness. So what does that mean? Well, the slope is almost 0. 1.9 times 10 to the minus third in decimal would be, let me see, 0.002 roughly. So the slope is 0.2%. Basically nothing. The efficiency is going up a tiny, tiny amount, but we're really hovering around 75% efficiency. And there are a lot of reasons for that. Students usually point out the spring scale deflection because we've talked a lot about elastic potential energy and Hooke's law by this point. So that takes energy to deform a spring like that. Students also point out the friction in the bearings. You can see how much the pitting and I don't know, how much the grabby nature of the bearings is causing the force to fluctuate and bounce right here. And the third obvious factor is the weight of the harness. The block and tackle itself, it takes energy to lift, and that's not the load. That's like the machine itself. So those three factors sort of add up to the 75% efficiency. I have all sorts of, concept sketches and areas for improvement. Maybe we could put a strain gauge on this instead of a mechanical spring scale and use the fancy statistical analysis. We analyze all sorts of simple machines like wrenches and hammers, seesaws, the traditional first class lever, wheel and axle. Let's see, this is a compound machine. We have a first class lever and a wedge as the wire cutters in here. And yeah, thanks for watching. See you in the next video.